National Electrical Code Section 310.4 addresses conductors in parallel. This section of the code outlines specific requirements that must be met when conductors are connected in parallel to form a single equivalent conductor. One crucial aspect covered by 310.4 pertains to the equipment grounding conductor size relative to the ungrounded conductors in an alternating current circuit. The general rule stated in 310.4 mandates that the equipment grounding conductor must be the same size or larger than the ungrounded conductors. In the context of parallel conductors, this implies that if you intend to parallel number 1 copper conductors, the equipment grounding conductor should be at least a number 2 copper conductor. However, an important exception exists within 310.4b that could potentially alter this requirement. This exception provides leeway in situations where the load served is considered nonlinear. Nonlinear loads introduce harmonic currents into the electrical system, which can disproportionately load the neutral conductor and, consequently, the equipment grounding conductor. The exception in 310.4b acknowledges this phenomenon and permits the use of smaller equipment grounding conductors when dealing with nonlinear loads. To ascertain whether a violation of 310.4 has occurred in a specific design, a more in-depth understanding of the load characteristics is necessary. If the load is indeed nonlinear, the designer might have a valid justification for utilizing number 1 copper conductors in parallel for the grounded conductor, leveraging the exception provided in 310.4b. Conversely, if the load lacks nonlinear characteristics, the use of number 1 copper conductors in parallel would likely contravene the requirements of 310.4. Now let's delve into the specifics of parallel conductors as outlined in the National Electrical Code, or NEC. Section 310.4 of the NEC provides the comprehensive guidelines. Firstly, conductors of the same material, for example copper or aluminum, must be used. Mixing different conductor materials in parallel is prohibited. Secondly, all parallel conductors must have the same length to ensure equal current distribution among them. Thirdly, conductors must have the same conductor size and circular mill area. Fourthly, conductors must have the same insulation type. Fifthly, all conductors must be terminated in the same manner. Utilizing compatible connectors and ensuring proper torque is essential. It's crucial to consult the manufacturer's instructions for the specific connectors being used. Now let's discuss about the equipment grounding conductor and the role it plays in electrical safety. The equipment grounding conductor, often referred to as the EGC, is a vital component of an electrical system safety mechanism. Its primary function is to provide a low impedance path for fault current to return to the source, typically the electrical panel or transformer. This low impedance path facilitates the rapid tripping of overcurrent protective devices, such as circuit breakers or fuses, in the event of a ground fault. By promptly clearing the fault, the equipment grounding conductor minimizes the risk of electrical shock hazards and prevents damage to equipment. Without an effective equipment grounding conductor, fault currents could flow through unintended paths, potentially energizing conductive surfaces and creating dangerous conditions. Now let's discuss about nonlinear loads. Nonlinear loads are electrical loads that draw current in a non-sinusoidal manner. This means that the current waveform is not a pure sine wave, but instead contains harmonics. Harmonics are currents or voltages that are integer multiples of the fundamental frequency, which is typically 60 Hz in North America. Common examples of nonlinear loads include electronic devices such as computers, LED lighting, variable frequency drives, and uninterruptible power supplies. These devices often use switching power supplies that draw current in short, sharp pulses, resulting in a distorted current waveform. The presence of harmonics in the electrical system can lead to a number of problems. Firstly, harmonics can cause increased heating in conductors, transformers, and other electrical equipment. This is because the harmonics contribute to the root mean square, or RMS, current, which is the effective value of the current. Secondly, harmonics can cause voltage distortion, which can affect the performance of sensitive electronic equipment. Thirdly, harmonics can cause interference with communication systems and other electronic devices. Now let's discuss about the exception in 310.4b. The exception in 310.4b of the National Electrical Code, or NEC, provides a specific allowance for reducing the size of the equipment grounding conductor when serving nonlinear loads. This exception recognizes that nonlinear loads can generate harmonic currents which disproportionately flow through the neutral conductor and potentially the equipment grounding conductor. To apply this exception, several conditions must be met. Firstly, the load must be identified as nonlinear. Secondly, an analysis must be performed to determine the harmonic content of the load current. Thirdly, the equipment grounding conductor must be sized based on the calculated harmonic current, but in no case smaller than specified in Table 250.122 of the NEC. It's essential to consult with a qualified electrical engineer to accurately assess the harmonic content and determine the appropriate equipment grounding conductor size. This approach ensures compliance with the NEC while providing adequate protection against fault currents. If the load is determined to be nonlinear, then a harmonic analysis should be performed to determine the amount of harmonic current that is present. The equipment grounding conductor can then be sized based on the harmonic current, but it shall not be smaller than as specified in Table 250.122. Table 250.122 provides the minimum size of equipment grounding conductors based on the rating of the overcurrent protective device in the circuit. This table ensures that the equipment grounding conductor is adequately sized to carry fault current and protect equipment and personnel. Now let's look at the different ampacity tables within Article 310 of the National Electrical Code, or NEC. Article 310 contains ampacity tables that provide the allowable current carrying capacity of conductors based on various factors. These tables are essential for determining the appropriate conductor size for a given application. Table 310.15b16 is one of the most commonly used ampacity tables. It provides the allowable ampacities of insulated conductors rated up to 2000 volts based on the conductor's insulation type, size, and ambient temperature. This table is typically used for general wiring applications in buildings and structures. Another important table is 310.15b17, which provides ampacities for single conductors in free air. This table is used for conductors that are not enclosed in raceways or cables, such as those used in overhead power lines. The ampacities listed in these tables are based on specific conditions, such as the ambient temperature, the number of conductors in a raceway, and the type of insulation. If the actual conditions differ from those specified in the tables, correction factors must be applied to determine the allowable ampacity. Now let's discuss about the specific ampacity correction factors and adjustment factors. Ampacity correction factors and adjustment factors are crucial considerations when determining the appropriate conductor size for an electrical installation. These factors account for various conditions that can affect a conductor's ability to dissipate heat and maintain its rated temperature. Correction factors are applied when the ambient temperature exceeds the temperature rating of the conductor's insulation. These factors reduce the allowable ampacity of the conductor to prevent overheating and potential damage. Adjustment factors, on the other hand, are applied when multiple current-carrying conductors are installed in close proximity, such as in a raceway or cable. The close proximity of these conductors can cause them to heat each other, reducing their overall ampacity. The National Electrical Code, or NEC, provides tables and guidelines for determining the appropriate correction and adjustment factors for various conditions. It's essential to carefully consider these factors to ensure that conductors are properly sized to carry the intended load current without exceeding their temperature rating. Now let's talk about conductor terminations and the importance of proper termination techniques. Conductor terminations are the points where conductors are connected to electrical equipment, such as circuit breakers, switches, and receptacles. Proper termination techniques are essential for ensuring reliable electrical connections and preventing overheating and potential hazards. Firstly, conductors should be stripped to the appropriate length to ensure proper contact with the termination point. Secondly, terminations should be tightened to the manufacturer's specified torque to provide a secure and reliable connection. Thirdly, antioxidant compounds should be used on aluminum conductors to prevent oxidation and maintain a good electrical connection. Fourthly, terminations should be inspected regularly for signs of corrosion, looseness, or damage. Improper terminations can lead to increased resistance, overheating, and potential electrical failures. Now let's look at the role of a qualified electrical engineer in electrical system design. A qualified electrical engineer plays a critical role in the design and implementation of electrical systems. These professionals possess the knowledge, skills, and experience necessary to ensure that electrical systems are safe, reliable, and efficient. They are responsible for conducting load calculations, selecting appropriate conductors and equipment, designing grounding systems, and ensuring compliance with relevant codes and standards. Electrical engineers also play a key role in troubleshooting electrical problems and developing solutions to improve system performance. Their expertise is essential for ensuring the safety and reliability of electrical systems in residential, commercial, and industrial settings. Now let's talk about the consequences of violating NEC 310.4. Violating NEC 310.4 can have serious consequences, potentially leading to electrical hazards, equipment damage, and even legal ramifications. If conductors are not properly sized and installed in parallel, they may overheat, leading to insulation breakdown, arcing faults, and fires. Additionally, improper grounding can increase the risk of electrical shock hazards and damage sensitive electronic equipment. Failure to comply with the NEC can also result in fines, penalties, and legal liability in the event of an electrical incident. It's essential to adhere to the requirements of NEC 310.4 and other relevant codes and standards to ensure the safety and reliability of electrical installations. Also keep in mind that local amendments can take place to further enforce regulations. Now let's look at real-world examples of NEC 310.4 violations. One common example of a NEC 310.4 violation involves the improper paralleling of conductors in a commercial building. For instance, if a contractor attempts to parallel undersized conductors to serve a heavy load without properly calculating the ampacity and applying the necessary correction and adjustment factors, it could lead to overheating and potential fire hazards. Another example involves the improper grounding of equipment in an industrial facility. If the equipment grounding conductor is not sized correctly or is not properly connected, it could increase the risk of electrical shock hazards and equipment damage. These real-world examples highlight the importance of adhering to the requirements of NEC 310.4 and other relevant codes and standards to ensure the safety and reliability of electrical installations. Now let's look at the different resources available for understanding NEC 310.4. Several resources are available to help understand NEC 310.4 and its requirements. Firstly, the National Electrical Code, or NEC, itself is the primary resource. The NEC provides the complete text of 310.4, along with related definitions, tables, and examples. Secondly, electrical engineering textbooks and reference manuals often include detailed explanations of NEC 310.4 and its application. Thirdly, online forums and discussion groups can provide valuable insights and perspectives on NEC 310.4 from experienced electrical professionals. Fourthly, continuing education courses and seminars on electrical codes and standards can help deepen understanding of NEC 310.4 and its practical implications. It's essential to utilize a variety of resources to gain a comprehensive understanding of NEC 310.4 and ensure compliance with its requirement. Now let's review grounding versus bonding. Grounding and bonding are two distinct but complementary concepts in electrical safety. Grounding refers to the intentional connection of an electrical system or equipment to the earth. This connection provides a low impedance path for fault current to return to the source, facilitating the rapid tripping of overcurrent protective devices. Grounding helps to minimize the risk of electrical shock hazards and prevent damage to equipment. Bonding, on the other hand, refers to the connection of metallic parts of an electrical system or equipment to create an electrically conductive path. Bonding helps to equalize the voltage potential between different metallic parts, reducing the risk of electric shock if a fault occurs. Both grounding and bonding are essential for ensuring the safety and reliability of electrical systems. Now let's talk about conductor insulation types. Conductor insulation types play a crucial role in the safe and reliable operation of electrical systems. The insulation provides a barrier between the conductor and its surroundings, preventing electrical current from flowing where it's not intended. Various insulation types are available, each with its own set of properties and applications. Some common insulation types include THHN, THWN, XHHW in use. THHN is a thermoplastic high heat resistant nylon coated insulation commonly used for general wiring applications. THWN is a thermoplastic heat and water resistant nylon coated insulation suitable for wet and damp locations. XHHW is a cross-linked polyethylene high heat and water resistant insulation offering excellent electrical and mechanical properties. Use is an underground service entrance cable designed for direct burial applications. The appropriate insulation type should be selected based on the specific environmental conditions and application requirements. Now let's discuss neutral conductors in three-phase systems. Neutral conductors in three-phase systems play a critical role in providing a return path for imbalanced currents. In a balanced three-phase system, the currents in each phase are equal in magnitude and 120 degrees apart, resulting in a net current of zero in the neutral conductor. However, in an imbalanced system, the currents in each phase are not equal, resulting in a non-zero current in the neutral conductor. The neutral conductor is sized to carry the maximum unbalanced current that is expected to flow in the system. In some cases, the neutral conductor may need to be larger than the phase conductors to accommodate the unbalanced load. Nonlinear loads can also cause increased current in the neutral conductor due to the presence of harmonic currents. Now let's discuss how to prevent voltage drops. Voltage drop is a reduction in voltage along a conductor due to the impedance of the conductor. Excessive voltage drop can cause equipment to malfunction, reduce the efficiency of electrical systems, and even damage equipment. To prevent voltage drop, several measures can be taken. Firstly, conductors should be sized appropriately to minimize the impedance of the circuit. Secondly, conductors should be run as short as possible to reduce the overall impedance. Thirdly, multiple conductors can be run in parallel to reduce the impedance of the circuit. Fourthly, voltage drop compensation devices can be used to boost the voltage at the load end of the circuit. Now let's talk about the different types of overcurrent protective devices. Overcurrent protective devices, or OCDs, are essential components of electrical systems designed to protect against overcurrent conditions such as short circuits and overloads. These devices interrupt the flow of current when it exceeds a predetermined level, preventing damage to equipment and reducing the risk of electrical hazards. Common types of OCDs include circuit breakers and fuses. Circuit breakers are electromechanical devices that automatically trip and interrupt the circuit when an overcurrent condition is detected. Fuses, on the other hand, are single-use devices that melt and break the circuit when the current exceeds their rating. Both circuit breakers and fuses are available in various sizes and types to accommodate different applications and protection requirements. The selection of the appropriate OCD depends on factors such as the circuit's voltage, current rating, and the type of load being protected. And finally, let's review conductor dating and ambient temperature correction factors. Conductor dating and ambient temperature correction factors are essential considerations when determining the appropriate conductor size for an electrical installation. These factors account for the effects of ambient temperature and the number of conductors in a raceway and the conductor's ampacity. When the ambient temperature exceeds the temperature rating of the conductor's insulation, the conductor's ampacity must be reduced to prevent overheating and potential damage. The National Electrical Code, or NEC, provides tables and guidelines for determining the appropriate correction factors for various ambient temperatures. Similarly, when multiple current-carrying conductors are installed in a raceway, their ampacity must be reduced to account for the heating effect of the other conductors. The NEC provides adjustment factors for different numbers of conductors in a raceway. By applying these dating and correction factors, engineers and electricians can ensure that conductors are properly sized to carry the intended load current without exceeding their temperature rating.